and welcome to CO 738 Probabilistic Methods. Today we'll be discussing the crossing lemma. So what is the crossing lemma? Well, first let's introduce crossing number. Recall that a graph G is planar if it can be drawn in the plane without crossings. The crossing number of a graph G, denoted CR of G, is the minimum number of crossings over all drawings of G in the plane. From Euler's formula, you might recall that if G is planar, then the number of edges is at most 3 times the number of vertices, minus 6. From this, you can derive a rather immediate corollary that the crossing number of a graph G is at least E, the number of edges of G, minus 3 times the number of vertices of G, plus 6. And why is that? So you might want to pause the video and do this proof. So what is the proof? Well, it's by induction on the number of edges. Namely, we could assume that the number of edges is at least strictly greater than 3v minus 6, and then by Euler's formula there would exist an edge with a crossing. And then we would delete it and apply induction, and this would give you the desired result. So essentially this corollary says that for every edge above this Euler's formula limit, there must be at least one additional crossing. So that's a rather trivial lower bound, but the previous bound is actually terrible for dense graphs. So in particular, the crossing number of the complete graph Kn is more on the order of n to the fourth, so quartic, while the previous bound gives quadratic. So we won't go into the details as there are conjectures about what the exact crossing number of Kn are, but it is known that it is on the order of n to the fourth. So a natural question is, can we do better? Can we do better for these dense graphs? And the answer is yes, and it's known as the crossing lemma. So if G is a graph where the number of edges is at least 4 times the number of vertices, then the crossing number of G is at least the number of edges cubed over 64 times the number of vertices squared. So you will note that if you plug in for Kn, where number of edges is more like n squared, then this would indeed give you something on the order of n to the fourth. So this is much better for dense graphs. All right. So what do we know about this? Well, it was originally found by Itai, Quattell, Newborn, and Szemeredi in 1982, and independently by Leighton in 1983. Today we will be giving a short probabilistic proof of the crossing lemma. So this is really the beauty. We will use probability to improve this bound. So we're going to actually use that trivial lower bound, but some probability to get this much better bound. So again, this is something we've seen. The key idea is we'll choose a subset of the vertices. We'll let X be a subset of the vertices of G, obtained by choosing each vertex of G independently with probability P. P to be determined later for optimality. So we choose this random subset. And then what do? We will let H be the graph induced on that subset of vertices. And by the previous theorem, the crossing number of H had to be at least E minus 3v of H. Plus 6, don't care about the plus 6. I'll rewrite it as the crossing number of H minus E plus 3 times V of H is at least 0. And this holds crucially for every H. So no matter what random subset I get, I always get this bound, that this formula is always at least 0. So why is that useful? Well, then it means that the expectation of that random variable is always at least 0. So it is 0 since it's always 0. And now we can rewrite this, so using linearity of expectation, we can break up that random variable linearly and rewrite to get the expected crossing number of H has to be at least the expected number of edges of H minus 3 times the expected number of vertices of H. So now all that remains is to calculate these various expectations. So the expectation of the number of vertices of H, well, since each is picked with probability P by linearity of expectation, we get P times the number of vertices of G. For edges, you need to pick both ends, so the expected number of edges is P squared times the number of edges of G. Sorry for the typo there, that last H should be a G. So we know it's P times the number of vertices and P squared times the original number of edges. And what about for the crossing number? Well, crucially, you can try to upper bound the crossing number. So we originally knew that there was an optimal drawing of G with the crossing number of G crossings. So if we just take that drawing, how do the crossings survive? Well, since the crossings are 2 edges whose ends are disjoint, we need all 4 of the ends to survive. So this tells you that in that drawing, we would have an expectation at most p to the 4th times the crossing number of G. crossings. And that gives you an upper bound on the expected crossing number of h. So there may end up being better drawings once we delete edges and vertices as such, but this gives us at least an upper bound. So now we can plug that all into the previous equation. So before we knew that the expected number of crossings of h, which is upper bounded by p to the fourth crossing g, had to be at least the expected number of edges of h, which is p squared e of g, minus 3 times the expected number of vertices of h, which is 3p v of g. So just dividing by p to the fourth there, you get that formula, and then that simplifies to the number of edges over p squared, minus 3 times the number of vertices over p cubed. So we get this somewhat strange lower bound, where again p was arbitrary. So now we can optimize. So it turns out it's not exactly optimal, but it's decent for our formula. We'll set p to be 4 times v over e of g. And importantly, that's at most 1 by assumption, right? We assume the number of edges was at least 4 times the number of vertices. So that is indeed a valid probability. And then if you just plug that in, you'll end up getting an e cubed and a v squared on bottom for each term. And you'll get a 16th minus 3 64ths, which will be a 64th. So you'll get that the crossing number is at least e cubed over 64 v squared as desired. So this is quite a nice proof. And again, why does it work? Essentially, the idea is that we use that old, somewhat trivial bound, which was terrible for dense graphs, but is actually quite useful for sparse graphs. So if you had more like a linear number of edges, then this would actually be quite useful. And then the idea is, by taking a random subset, if we choose the randomness there, the parameter p, to be quite small, so that the expected number of edges is roughly more like the expected number of vertices, so it is indeed sparse, then applying this trivial bound will actually be useful. So that's somehow the key, is by passing to the random subset, a sparse random subset, we can indeed make a lot more out of that graph. We expect crossings there, so there have to be many more crossings in the original. So that's quite a nice use of probability to prove the crossing lemma. Now we will go on for the rest of the lecture and tell you some nice consequences of the crossing lemma. So one nice consequence is a short proof of the Szemeredi-Trotter theorem from 1983. So it says the following. If P is a set of n distinct points in the plane and L is a set of m distinct lines on the plane, then the number of incidences between P and L, so what is that? I mean the number of pairs, little p and little l, where p is a point, little l is a line, and the point little p is in L. So precisely what you think, these pairs of point line incidences. And the theorem says that this number is actually on the order of, is O of, so is at most, some constant times m to the 2/3, n times n to the 2/3, plus m plus n. So, of course we have maybe m and n as somewhat natural, but they get this nice term, instead of just m times n, which would be a trivial upper bound, we can get m to the 2/3 and n to the 2/3, an improvement over a trivial bound. So that's quite a nice theorem. And the theorem was originally, the proof was more complicated, but you secondly noticed that Szemeredi-Trotter is actually an easy consequence of the crossing lemma. So as I said, the original proof was more complicated. Here, it's something you can do in a page. So we'll go ahead and do it. So how do we do this? So again, this won't use probability. We already did the probability before. We're just going to apply the crossing lemma. So what does it give? How do we do this proof? We may assume without loss of generality that every line in L is incident to at least one vertex of P. So why is that? Well, if they're extra lines, they're not doing any incidences, so you could just delete them. That's fine. And now, where can we go from there? We'll let I denote the number of incidences, and we'll define a graph, right? So the crossing lemma was about graphs, so I need a graph. There's no graph yet. So here's the graph. We'll let the vertices of G be P, the points, the set of points. And we'll put an edge between 2 points P1 and P2 if and only if there exists a line, little l, where P1 and P2 are consecutive in the line. So consecutive among all those points. So basically for each line, you just look at all the points on it, assuming there's 2 or more, and you put an edge between the consecutive ones. So what does this give? Well, the number of vertices is clearly n, the number of points. And the number of edges is a little trickier to calculate, but what is it? Well, for each line, we would get P times intersect L minus 1, right? So if there's only one point, we don't get any edges, and we're assuming every line has at least 1 point. If you have more than that, you get the number of points minus 1, so you only get the edges in between. So if you sum that up over all lines little l, what does that give? Well, the first number just really sums up all the incidences, right? So it just ends up as I, the number of incidences, but we get this minus 1 for each line, so that's minus m, the number of lines. And now we want to apply the crossing lemma. The important point is the configuration of P and L naturally leads to a drawing of G, right? So we want some bound on the crossing number. This gives you maybe not the optimal drawing, but a pretty good drawing. And in that drawing, every crossing is an intersection of two lines in L, right? So all the edges lie on lines, so it has to be, two lines can only intersect in 1 point, so it's every crossing is an intersection of two lines in L, and the number of such pairs is m choose 2. So the crossing number of G, we know from this configuration, is at most m choose 2, which is, let's say, at most m squared over 2, so we don't really care about lower order terms. And now we're almost done. We just have to almost apply the crossing lemma. But there's an issue. Crossing lemma only works if E is at least 4 times V of G. So case 1, if E is smaller than that, if there just aren't many edges, well then I minus m, which is the number of edges, is at most 4n, so then I is at most m plus 4n as desired. So this kind of covers the case where somehow, the number of incidences is more linear in n and m. Then the case 2 is that E is indeed at least 4 times the number of vertices of G, and so we can apply the crossing lemma. So by that, we'd have m squared over 2 is at least the crossing number, which by the crossing lemma is at least the number of edges cubed over 64 number of vertices squared. And remember that the number of edges was I minus m, so we get I minus m cubed, and divided by 64n squared, where n's the number of vertices, the number of points. And now we're almost done, because now you can rewrite this, and what do you get? So you get a 32 and an m squared and an n squared, but we're going to take a cube root of that, so we get 32 to the 1/3, m to the 2/3, n to the 2/3, and then we had I minus m, so you get a plus m. So the number of incidences is the most on the order of m to the 2/3, n to the 2/3 plus m, in this case as desired. So in either case, we get this m to the 2/3, n to the 2/3 term. In the latter case, we get a plus m in both cases and a plus n in the first case, which altogether works to prove the Szemeredi-Trotter theorem. So it's quite a nice use of converting this point line configuration into a graph to apply the crossing lemma to. All right, so that was that. I want to mention one extension of this, which is quite nice, is about unit circles. So an analogous argument shows that the number of incidences between n distinct points in the plane and m distinct unit circles in the plane is on the same order. So why is that? It's essentially you run through the same argument. There is a slight point where two circles could actually intersect in 2 points instead of 1 as you get for lines, but that just changes the constant. So that's nice. I wanted to mention, though, this implies a very nice result that the number of unit distances determined by n points in the plane is on the order of n to the 4/3. So what I mean, if you had n points in the plane, how many pairs of them can be at a unit distance, or a distance of 1? So trivially you get, n squared, but this actually gives you n to the 4/3 as an upper bound. Why? Because you'd have these n unit circles, would make the unit distances, and you'd be looking at those incidences. So you'd set m to be n, and you get an n to the 4/3 above. And I will mention that Pack and Toth had shown in 1997 that Szemeredi-Trotter is sharp up to a constant factor. So there are examples where you kind of need this m to the 2/3, n to the 2/3, plus m plus n. And interestingly, Erdos in 1946 had conjectured that the number of unit distances should not be that. So it should be actually more like O of n to the 1 plus epsilon for any epsilon greater than 0. So it's known to be superlinear, but it shouldn't be too much superlinear, is the idea. And that's still actually open today, and the best bound is still this n to the 4/3 from the Szemeredi-Trotter theorem. So what we've covered so far, we've done the crossing lemma. It implies the Szemeredi-Trotter theorem with a remarkably short proof. So these proofs are all short and nice, and that can be used also in this old unit distance problem for the best known bound. Surprisingly, it also has applications in number theory. So Alekesh found several applications in 1997 of the Szemeredi-Trotter theorem in additive number theory. So I just wanted to go through those to, again, see the connections from these different points. So from graphs, crossing number geometry there, to point line incidences, back to number theory, all over the place. And the crossing lemma, the central heart of these, all can be done with a simple probabilistic proof. So first I'll mention one. It's quite nice. It's for any three sets A, B, C of real numbers, each of size S, then the size of A times B plus C, which more formally is AB plus C for little a and A, little b and B, little c and C, it's at least S to the 3 halves on the order of. So if we kind of take these product plus sum, we're saying there's actually guaranteed to be a lot of them no matter what these sets are. So that's quite an interesting theorem. It's not really clear how you would prove that, and we'll go through the proof, but how would you prove that, especially without the crossing lemma? And here's another, also quite nice, is similar. It says if A and B are sets of S reals, then at least one of the following holds. Either A plus B, that's the sum set, is at least S to the 5 quarters on the order of, or the product set A times B is on that order, S to the 5 quarters. So this is quite nice, is saying that either the sum set or the product set has to be large. So you get either a lot of distinct products or a lot of distinct sums. And this too will follow quite easily from the Szemeredi-Trotter theorem. So let's do the first one. So proof of the first, we're interested in, I'll call it R, this A times B plus C, and I'll make little r the size of R. So we want to apply Szemeredi-Trotter, so you need points and lines. What should the points be? Well, for the points, I'm going to take A comma T, where A is in A and T is in R. So we're going to think of these as points, which are the first coordinate being in A and the second coordinate being this product sum thing. And the lines, I'll be T equal Bx plus C, where B is in B and C is in C. So we'll use B and C for B will be, the slope, and C will be the y-intercept there. So that's kind of natural, as A times B plus C is of that order. So you think of A's as the variable, somehow B's is the slope, and C's is the intercept, naturally gives points and lines. And then you can note that P is actually a set of n points in the plane, where n is actually S times R. So there's S choices for A, and then we know there's R choices for T. L is a set of M equals S squared lines in the plane, right? Because for the choices for B, there's S of M, there's S choices for C, and those all give different lines. And now we're almost done. The question is, how many incidences do we have? Well, each line, y equal bx plus c, I claim is incident with a lot of points. So y, I claim it's incident with s points of p, i.e., so how do you get a point? Well, we'd have to plug in some value for x. So in particular, we have to plug in one of the a's, and then that immediately gives a plus c, ab plus c, so it's incident with those, and those are all distinct points. So that's actually an equality, and so we get that s cubed is equal to I. So each of the s squared lines is incidence with s points. So there are s cubed incidences, and by the Szemeredi-Trotter, that's at most 4 times, m to the 2/3, m was s squared, n to the 2/3, which is sr, plus s squared plus sr, m and n there. And now you look at that right-hand side, and you'll realize that if r was little o of s to the 3/2, so if it was smaller than what we were assuming, what would happen? Well, really that cleans up to an s squared times r to the 2/3, so that first term would be little o of s cubed, and then the other terms would be as well. They'd be s squared and little o of s to the 5/2. So altogether, the right-hand side would be little o of s cubed, which would be a contradiction. So indeed, we're guaranteed that r actually has to be on the order of s to the 3/2 or more, and that concludes that first proof. And now I'll prove the second. So this is the last thing of the lecture. It's quite similar. So here I'm going to let r be the size of a plus b, the sum set, and t be the size of a times b, that's the product set. And now I have to define points and lines. So here it's a bit trickier, but I'll define the points to be these pairs CD, where C is the sum, a plus b, and d is in the product set, a times b. And now the lines will end up choosing y equal a times x minus a prime, so parentheses there, and where a and a prime are both in a. So we're somehow going to use the lines coming only from a. And now the idea is quite similar, that P is a set of points, of course, in the plane. How many are there? There's R choices for the first and T choices for the second, so there's RT points. And similarly, there's S squared lines in the plane, because there are S values for possibilities for A, so A and A prime each have S choices, so you get S squared. And now, what about the incidences? So we need some lower bound of the number of incidences, so I claim that this line y equal ax minus a prime is incident with at least s points of P. Namely, if we take a prime plus b as our point, then when you subtract a prime, you get b, and you get ab as the other. So indeed, a prime plus b is in the sum set, and ab is in the product set, and that works for any b and b, and those are indeed different points. So each line is incident with at least s points. So now we get that by Szemeredi-Trotter. So again, we just established that s cubed was at most I, the number of incidences. And that's at most this 4 times, we have an s squared 2/3, RT times 2/3 plus s squared plus RT. So what do we get there? So the number of incidences is at most these values. So if you work them out, so what are we assuming here? If R was little o of s to the 5/4 and T was little o of s to the 5/4, that would be the assumption, right? So we're happy if one of them is large, but if they're both small, then look at that, right? So again, we get an s to the 4/3. If they're both at most 5/4, then that will be little o of s cubed. And indeed, the two lower terms will have s squared and something that's little o of s to the 5/2. So once more, the right-hand side is little o of s cubed, which is a contradiction. So this is quite a nice proof. So both of these additive number theory ones are nice proofs. You just pick points and lines. You can calculate the sizes of those. You pick them in a way that there's a lot of incidences, and Szemeredi-Trotter then ends up giving you kind of a bound from that. So then we end up knowing that somehow, here the sum set of the product set has to be large. Previously it was that sum/product set had to be large, and both work out quite nicely. So that's all for today. Today we covered the crossing lemma, quite a nice result in topological graph theory on the crossing number and a lower bound there. The idea being that we could take a trivial one and using probability and randomness, only applying it to somehow the sparse random subsets, get a much better bound for dense graphs. We applied that to give a short proof of the Szemeredi-Trotter theorem, which in turn we then applied in additive number theory to prove some nice results about sum and product sets. So that's all for today. Until next time, see you then!